Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have Unlabeled here today from University of Texas, Austin. He's finishing up his PhD thesis with Ray Mooney, who actually introduced me to machine learning N years ago for some big hand. And he's going to talk about, I guess, better ways of using data, better ways of doing cheap supervision and so on. So go ahead.
Ensemble classifiers to reduce supervision. And I'd first like to acknowledge all my collaborators who have contributed to this work in one way or the other. If you can't hear me back there, I would recommend coming up front because it's not going to get much louder from here. So most of the motivation for our work is based on the fact that acquiring supervised training data for learning tasks is to build accurate classifiers or models is often difficult or expensive. So either you have cases where you have limited amounts of training data, or quite often you can acquire additional training data, but there's a cost associated with this acquisition. And we study this problem in three settings. The first is what I would call just the pure supervised learning setting, where we're given a set of training instances, which I represent abstractly here by this matrix, where every row corresponds to a set of to an instance represented by a set of features and a class label. And then we train a learner on these instances to produce a classifier. And given an unlabeled test instance, the classifier is required to produce a prediction for the label of this instance. And the task here is usually to maximize the accuracy of predictions on these test instances. So in various domains such as personalization, it is really critical to achieve a very high performance with very little feedback from the user, because a user would stop using a system in such cases if you didn't get immediate feedback. So in such domains, it's really critical to maximize the utility of small training sets. So this is one of the settings that we study. The second setting is the active learning setting, in which we, in addition to the training examples, we also have access to a large pool of unlabeled instances. And here, what the learner can do is select instances to acquire labels for. And typically, the learner wants to select instances so that it would improve the accuracy of the classifier once trained on these instances. So a typical domain here would be a case like web page classification, where it's easy to get access to a large number of unlabeled examples or unlabeled web pages, but there is an effort expended at labeling each of these web pages. And the aim is sort of to build the most accurate classifier by spending the least amount of effort here. And the third setting is sort of a related setting, which is a more novel task that we've introduced, which we call active feature value acquisition. And here we basically have class labels for the instances, but instances may be missing feature values, right? And in this setting, the learner can select instances for which to acquire complete information. And again, you want to select information that would be most beneficial to improving the accuracy of your current classifier. So the main contribution of the work, and what I'm going to talk about, is a new method for building an ensemble of classifiers, which helps reduce the amount of supervision required in each of these three settings. And the bottom line is basically we introduce more accurate models than existing methods at lower costs of acquiring data. So here's an outline of this talk. I'll first go over some background on ensemble methods and ensemble diversity, and I'll introduce our specific method for constructing ensembles called Decorate. And then I'll talk about experiments in each of these three settings that I just mentioned, and end with some future work and conclusions. So to begin with, just to set up what ensembles are, so basically an ensemble or a committee of classifiers is a set of classifiers whose individual decisions are combined in some way to produce a classification for a new instance. And typically, ensembles tend to be more accurate than the base classifier, which is basically the individual classifiers that the ensemble is made out of. And There have been many methods proposed for constructing ensembles. The most popular approaches in the literature are bagging and boosting. And I won't spend too much time on the details of this. I'll give you the one-line descriptions. Basically, in bagging, you generate a committee of classifiers that are trained on different samples of the original training data. Whereas in boosting, you learn a series of classifiers where each one focuses on the errors made by the previous methods, by the previous classifier. So I'll say a little more about boosting since it's a very popular method, and when I refer to boosting in this talk, I'm talking about the AdaBoost M1 algorithm. And this is an algorithm that's been shown to be very effective, and it's been extensively tested by various researchers. And in particular, applying AdaBoost to decision trees has been very successful, and some people consider it to be one of the best off-the-shelf generic inductive classifiers. However, AdaBoost tool has a couple of drawbacks despite its various strengths. And the first is that it fails to perform well when given insufficient data. And the second is it can often perform worse than just the base classifier when we have noise in the training data. So there is, yes? There are various versions to deal with sort of noise, but I don't think there's been a sort of a consistent improvement shown on both that perform well on both insufficient or small training sets as well as noise in the training data. But I mean, if you have a specific method you want to talk about, we can.
The original I think it was by Mika, I think it's Sebastian Mika.
Okay, well, I can take a look at that. But in general, so I mean, most of these results come from the boosting theory. I mean, the fact that it doesn't do well on insufficient data is sort of from the boosting theory. But so there is sort of still room to improve here, and the need for developing other ensemble methods. And we find the key here lies in the concept of ensemble diversity. So basically, it's only useful to combine classifiers if the individual classifiers disagree on some inputs. And we refer to this disagreement or the measure of disagreement in an ensemble as the diversity of the ensemble. So in the case of regression, where mean squared error is used to measure accuracy and variance is used to measure diversity, it has been shown that the ensemble generalization error can be decomposed into these two terms, which is the average error of the ensemble members and the average diversity of the ensemble. And what this result implies is that increasing diversity while maintaining the error of each of the ensemble members should lead to a decrease in the ensemble error. So for the task of classification, which is what we're interested in, this simple linear relationship doesn't hold, but there's still a lot of work that sort of points in the direction that diversity is highly correlated with error reduction. So in particular, we use the notion of the disagreement in an ensemble, or the disagreement of an ensemble member with the ensemble's prediction as a measure of diversity. So more specifically, if CIX is a prediction of the ith classifier for a label of example X, and C star X is the prediction of the entire ensemble, then we can define the diversity of the ith classifier on example X by this term, which basically just checks if a particular classifier disagrees with the ensemble prediction as a whole. And then to measure the diversity of an ensemble of size M on a training set of size N, we average this term out. So this basically measures the probability that a particular classifier in an ensemble will disagree with the ensemble's prediction. So our approach is based on building ensembles that are consistent with the training data, but still try to maximize diversity as defined by this term. So I'll go into a little more of the details of our algorithm. So our algorithm, which is called Decorate, generates ensembles iteratively. And at each step of this iteration, we use artificially constructed examples, and which are then added to the training set to build a new classifier. And basically, these examples are selected and they're labeled in such a way so that they disagree with the current ensemble's predictions for these examples. And so now when we train a new classifier on this augmented data, we force it to be different from the current ensemble. And therefore, adding it to the current ensemble will also increase its diversity. Right? So while forcing diversity in this way, we still want to maintain some level of accuracy. So we have this additional criteria that we reject a new classifier if adding it to the existing ensemble decreases its accuracy in any way. And once we produce an ensemble to make predictions on unlabeled data, we just take a majority vote of the ensemble. Yeah. Sure.
So you choose the label that's going to hurt, right? And it could be wrong.
There is actually, so these are artificial examples, so there is no sense of right or wrong. I'll go a little more into the overview of the algorithm and talk about how these examples are constructed in the next couple of slides. So, yeah.
Classifiers are very simple or have very limited capacity.
So this is a generic approach can be applied to any base classifier. We applied it to decision trees in particular. You want to use a sort of a strong learner that can always fit the training data, despite having these artificial examples. So maybe you want to hold off for a couple of slides. So here's the overview of this algorithm. So we're given originally a labeled training set, and for now, I'll assume I have a source of artificial examples. I'll talk about how these are constructed in the following slides. So initially, we train our base learner on this labeled training set, and this gives us our initial classifier, which we add to our current ensemble. And then we take the current ensemble and use it to make predictions for these unlabeled artificial examples. And now what we do is we look at these labels and we probabilistically flip these labels. And now we train another classifier to fit both the original training examples and these artificial examples. And so this gives us a classifier C2, which we see both C1 and C2 have to be consistent on the training examples. So they're very similar on the training examples, but are forced to be very different on these artificial examples. And now this process can be repeated where we have the current ensemble, which is composed of both C1 and C2, producing labels for these artificial examples, flipping the labels, and retraining to get the third classifier. So in this way, we produce three classifiers which are all very similar on the training examples, but are forced to be very diverse on the artificial examples. So the one caveat here is we obviously reject classifiers if adding C3 to the ensemble reduced the error of the ensemble, reduced the accuracy of the ensemble, we would reject such a classifier. So at no point are we actually creating an ensemble that's less accurate than the base classifier.
How are you actually combining the classifiers?
For predictions, we just do majority vote. So we take the class probability memberships produced by each of the classifiers and average them out, and that's pretty. So here's a little more about the artificial data. So we generate these artificial examples at each iteration of this algorithm, and each example is sort of just picked from a very crude approximation of the training data, where for numeric attributes, we just compute means and standard deviations from the training data and generate values from the Gaussian defined by this. For nominal attributes, we compute the probability of occurrence of each of the distinct values and then generate values from this distribution. So once we generate an example, we label it in the following way, where we first find the class membership probabilities predicted by the current ensemble, and then we select labels such that the probability of selection is inversely proportional to the current ensemble's predictions. So why should this algorithm succeed? We had a couple of hypotheses here. The first is that the decorate ensembles should produce more accurate classifiers than just the base classifier, and this is based on the fact that combining classifiers is usually more accurate than individual classifiers, and we know that diversity plays an important role in the reduction of error. The second hypothesis is more specific to comparisons with other ensemble methods, and we basically believe that decorate should outperform bagging and boosting with when training sets are small. And here we know that both bagging and boosting sort of produce a diversity, but they do this by either subsampling or reweighting the given training examples. And so when the training sets are small, this limits the amount of diversity that you can produce with these methods. Whereas decorate ensures diversity on an arbitrarily large set of additional artificial examples. And so we would expect better performances in these cases. So now we'll talk more about just our experiments on the pure supervised learning setting. Yes, please.
So when the sets are small, though, you're going to learn right? If you generate a lot of examples and you have a very small set, you're not going to learn training. You're going to learn
So we generate as many examples as there are in the training. So the number of artificial examples is proportional to the size of the training set. So
have the problem.
well, yeah, but we make sure that we never are performing less accurately than the base classifier trained on the training set, right? So because the first classifier in the ensemble is basically just trained on the training set, right? And each successive element is sort of you add, as you say, you can think of it as adding noise, but you're still sort of constrained to covering the training set. So you can think of it as finding different hypotheses in the version space that are consistent with the data but are sort of very far apart. Yeah.
When you say you never decrease the training, is it the training?
I mean training, yes. So it is possible to overfit, and it doesn't necessarily mean decreasing accuracy on the generalization.
On the training.
On the training set, yes. So we ran experiments on 15 data sets from the UCI repository, and so these vary in the number of examples and the number of classes and features, etc. So just a few details on the experiments. We compared our algorithm Decorate with bagging, boosting, and J48, which is just the Java implementation of C4.5. And we used J48 as our base learner for all the ensemble methods with an ensemble size of 15 for each of these methods. And all our results are averaged over 10 complete runs of tenfold cross-validation. So we generated learning curves for each of these data sets to test the performance on varying amounts of data. And here we selected the percentage of the total available data as our points on the learning curve. And we summarize our results over all data sets for each of these points.
That slide flew by so fast.
Oh, sorry. So here are a summary of our results. This is basically Decorate compared to the base classifier. And what we see is on the x-axis is increasing amounts of training data. And what each bar represents is the number of wins versus losses on all 15 data sets. So what we noted is that Decorate almost always improves on the base learner, given any amount of data. Okay, so these wins and losses are just absolute wins and losses. So
by one, you also call it a win. In other words, if for data set 7, if Decorate 1 better than J48, you'll count it as a win.
You mean 1 percentage point better?
One example.
Yeah, in this case, it's just absolute average accuracies. But we also, if you look at our papers, we've also looked at statistically significant wins and losses. And the trends that are the same. I'm just presenting these because it's easier to show wins and losses this way than wins, draws, and losses. But so here's a comparison of Decorate versus bagging. So we had expected to see significant improvements with small test sets, but we also noticed that with small training sets. But we also noticed that we have, we sort of do better than bagging throughout the learning curve. But as you'll note, with increasing amounts of data, this differences become smaller. And here's our comparison with boosting, where again we see that Decorate produces more accurate classifiers for small training sets, though the trend seems to be reversed after about 75% of the data. And what we should notice, even with larger amounts of data, the performance is still very competitive, where at 100% of the data sets, with 100% of the data, Decorate still has higher accuracies on 6 of the 15 data sets. And I'll talk more later about other experiments that we ran to show that they are really comparable on large data sets.
Just a few hundred examples, though, still. Right?
Yes, in most of these cases, yes.
So 1% is tiny, it's like 6 examples.
In some of the data sets, yes. So far we've just looked at these summary statistics over all the 15 data sets, but we can actually look at individual learning curves to get a better idea of the effectiveness of these data, of these methods. So here's the curves for the labor data set, where we see decorate, which is the line in green, sort of significantly doing better than all the other methods on this data set. What we should note here is this is a fairly small data set. It's just 60 examples. And as we predicted, in such cases, both bagging and boosting have trouble creating diverse ensembles. And so we'd expect to see this sort of performance here. What is more typical is an example like this, which is the cancer data set, where we see, given large amounts of data, the performance of these different methods sort of converge. But what's important to note is that, with few examples, basically the rate of learning is much higher for decorate. So in this case, with just 6 examples, we acquire an accuracy of greater than 92%, whereas which is much better than the other methods.
How does the standard learner do?
So the standard learner is a few points below 70. Is a few points below the first point of bagging. So I think it's about 72% on that point.
I don't get the intuition of why this, for the very small number of training samples,
Yeah.
you have so little data to sort of substantiate that your models and the fake data are right. I don't, can you give intuitively where the power comes from?
Yeah. So it's not that critical to have accurate models of the artificial data. The important thing is that we're sort of forcing things to be forcing classifiers to be different on these artificial
like
data.
On the previous one, we only had like 5 or so. Like
Yeah.
that big jump at 3 samples. Isn't it so many models that arbitrarily match those 3 samples? And 3 samples don't give you enough information on the data that's good artificial data. I don't see where it's working. I don't see where the
Yeah. So well, the power is really coming from not necessarily modeling the data correctly for the artificial examples, but really forcing the classifiers to still cover these 3 examples, but having hypotheses that are very different from each other, right? So the artificial examples are really critical for forcing diversity rather than it's not really that critical to have very accurate models of these. So even as it stands, our model for the artificial examples is very crude. It's you're taking a very simple approximations. But it does work in practice very, very effective.
So can you use this as a form of regularization?
Exactly.
So that would be one view of it.
You're limiting the space of functions essentially, and we have very small number of examples. That's what regularization is doing too.
Yeah.
So, just to get an idea, how many parameters does your system have? Like for this example, how many numbers are you training?
How many
Parameters?
how many numbers am I training on? You mean the algorithm itself is? I mean, you just specify the number of the size of the ensemble you want to build, right? There are.
You might have a parameter set for your model, right?
What kind of parameters are you talking about? So basically, this is just a general method applied to any Bayes learner. In this case, it's the learner itself is decision trees, right?
So there must be some parameters to specify what a decision tree is. For example, you have questions: is this number greater than or less than? Or you must store something when you store a model, right?
Oh, okay. So are you asking about the complexity of the models built?
Well, I guess so. And just how many parameters do you encode your model?
We actually haven't looked at the complexity of the models, but I mean, basically, all the ensemble methods sort of give rise to more complex models than just using single. Yes.
Well, let me follow up on one previous question. All of you are using the same Bayes learner?
Yeah, they are using the same method.
You all have the same number of Bayes learners?
Yes.
So the same
Well-
number of parameters held constant across the 3 methods?
Yes. So well, basically, in Decorate, you can have less than the specified number of Bayes learners, because if you fit the data very accurately, and the artificial examples are not being covered by a new classifier. Basically, the rejection criteria, that you're not adding a classifier if it decreases your accuracy. You may end up building a smaller committee. It does happen in some cases, but it's not very frequent especially with little amounts of data, you will build the same size ensemble.
So you're choosing a number of iterations for AdaBoost based on, I don't know.
It's a fixed number.
You're running the datasets and then you're choosing the numbers of classifiers for decorate and bagging based on.
No, we fixed it to 15 for all of them. So,
15 regardless of the size of the training.
yeah, we actually did run experiments on using larger ensembles of size 100 or so as well, which give you the same sort of results. And,
It's interesting. Compare this quite strongly regularized, like SVM or something. Just choose some classifier that.
right.
Because trees are okay, but there are other things.
Yeah, so that is something that we wanted to do. We've just applied this to simple to SMOs basically, and that was just with linear kernels, and we get the same sort of results. But I don't want to advertise that because I don't think that's a full study yet. But I mean, it would be really interesting. The thing is, once you start doing ensembles of SVMs, they start becoming a fairly computational. Oh, just yeah, okay, that would be another thing to consider. So basically, our approach is based on this claim that diversity fosters the reduction of error in ensembles. And to further support this claim, we ran additional experiments where we actually computed the Spearman rank correlation between diversity and ensemble error reduction. And basically, what that ensemble error reduction is the difference between the mean error of ensemble members and the error of the entire ensemble. And note here that there was a fairly strong correlation of this reduction in error with the diversity term. And this sort of bolsters our belief that increasing diversity is a good approach to reducing error. And we also ran further experiments actually computing the diversity of the ensembles produced by these different methods, which is decorate versus bagging and boosting on small training sets, where sort of to explain why we get these better performances there. And what this table summarizes is the win-loss records on diversity for all 15 data sets. And here again, we noted that decorate does indeed perform better by creating more effective or more diverse ensembles for these examples. So we've run a whole set of other experiments. I'll just give you some of the key comparisons. So we also ran an entire set of experiments with random forests, which is a more recent algorithm proposed by Bremen. And we see, again, more consistent improvements across the learning curve here. We also ran comparisons with boosting using large amounts of data. And by large amounts of data here, I'm just meaning the last point on the learning curve, which is 100% of the data, which as Chris pointed out, is not necessarily a very large data set. But we ran experiments on 33 of the available UCI data sets, looking at just the last point on these learning curves. And we see that in terms of statistically significant wins, there on 25 of these data sets, there really isn't much difference between the two methods. And in the remaining 8 data sets, they're sort of equally divided between decorate and AdaBoost. So far we've looked at decorate applied to improve classification accuracy in this purely supervised learning setting. And now I'll talk about a couple of settings where we can apply decorate in these active settings where the learner has some control over the acquisition of data. So I'll begin with traditional active learning, which is basically methods for selecting the most useful unlabeled example to be labeled for the learner. And here we typically want to select examples that we know would improve the accuracy of the current classifier. So in active learning, pool-based sample selection is probably the most common setting in which it's studied, where you choose the best instance from an available large set of unlabeled examples. And there are various approaches, obviously, to active learning. A very popular and theoretically well-motivated approach is QBC, or query by committee. And in this method, you basically generate a committee of classifiers, and an example is selected such that it causes maximum disagreement amongst the current committee. And in particular instantiations of these of the QBC algorithm have been done using bagging and boosting, and it's been shown to be quite effective. And these methods are known as query by bagging and query by boosting, respectively. So what we know is that for query by committee, it's useful to have an ensemble that is very diverse. So a diverse ensemble, which is one that effectively samples from version space, is one that's most effective for performing sample selection. And since we have this algorithm decorate that explicitly builds diverse committees, we think it was well suited for this task. And so what we wanted to verify is how effective are decorate ensembles for sample selection, and in particular, can this added diversity that we create select more informative examples than using bagging or boosting committees. So what we propose is this is a method called active decorate, which I describe here. So given a original set of labeled training examples, we first used decorate to produce our ensemble of classifiers. And then for each of the examples instances in the unlabeled set, we use the current classifiers in the ensemble to produce predictions for this example. And then based on these predictions, we assign a utility of acquiring the label for this instance. So I'll talk more about specific utility measures a bit later, but in general, if the committee agrees if all the members of the committee agree with the predictions, then there's probably less value in actually acquiring the label for this instance. Whereas in alternate cases where, for example here, where the committee is equally divided about the prediction of this label, it would be useful to actually acquire the class label to find out which one it is. So in such cases, we expect a high utility to be assigned to these instances. So this process is sort of repeated for each of the instances in the set, and then we basically select the instance with the highest utility, acquire its label from some expert, and add this instance to the training set. And now we can repeat this process. So
you throw away the ensemble and restart?
Yes, you throw away the ensemble and restart. Basically, query by bagging and query by boosting can be implemented in a similar way, where instead of decorate, we would plug in bagging or boosting. Right. So more specifically about the measure of utility, we evaluate the expected utility of acquiring an unlabeled example with respect to the current classifier based on the margins of the example. And here we define the margin as the difference between the highest and the second highest class membership probabilities as predicted by the current ensemble. Right. So here basically smaller margins would imply a greater uncertainty in your prediction of the class label. Right. And we would want to acquire such instances. I'll talk later about other measures of utility, but we'll first just look at the margin measure. So here are a few details of our experiments. We compared our method with both query by bagging, query by boosting, and decorate just using random sampling. And here again we used ensembles of size 15 and J48 as our base learner. So to generate learning curves in this active setting, we basically first treat all our examples as unlabeled examples. And then at each iteration, the active learner sort of selects a sample of points from this pool of unlabeled examples based on its measure of utility. And in the case of the passive learner, which is decorate here, we just select examples at random. So what I should point out is, based on the way these curves are generated, at the end of the learning curve, all the algorithms see exactly the same instances. Right? And what we're really looking at in these curves is how well are the different active methods ordering the set of instances in terms of its utility of acquisition. So typically you would see curves like this where both the active and random methods start off at the same point and end up at the same point. And the primary aim of active learning is to reduce the amount of data needed to acquire an accurate model or a model of a desired accuracy. So this is what we use to define our first metric that we use for comparing these methods, which we call the data utilization ratio. So what we do here is we define a target error rate as the error that decorate with random sampling can achieve on a given data set, which is basically the error averaged over the points at the end of the learning curve corresponding to the last 50 examples. And then we look at each of the active learners and see the smallest number of examples needed to acquire the same or lower accuracy. And then we just define the data utilization ratio as the number of examples required by the active learner divided by the number of examples required by Decorate. And what this metric reflects is how efficiently is your active learner utilizing data. So here's a slide just summarizing our results on this metric. And what we noted is that on all but one of the data sets, active Decorate produces greater improvements in accuracy over just Decorate using random sampling. And on average, it requires about 78% of the examples that Decorate would require. And this can be as low as 30%, as we see on the soybean data set. On the one data set that we didn't see improvements, which is the breast cancer data set, we sort of noticed there was a ceiling effect where none of the active methods were actually improving on the Decorate algorithm. So in comparison to the other active strategies, we noted that on 10 of the data sets, active Decorate does better than both other methods. And in fact, on some of the data sets, the other methods even failed to acquire the target accuracy of the Decorate algorithm. So I should point out here that Decorate itself achieves the target error rate with far fewer examples than is often available. So for example, on breast cancer, we acquired the target accuracy, or the learning curve tops out with just 30% of the available 630 examples. So improving on the data utilization of Decorate itself is a fairly challenging task. So the second metric that we looked at is percentage error reduction. And here we basically want to focus on, given a fixed amount of labeled data, what is the maximum improvement in accuracy? So we're interested in this reduction in error in the curve. And we compute this by looking at the percentage error reduction at each of the points over Decorate with random sampling, and then average these across the learning curve. And here's a brief summary of our results here, where we noted that on all data sets, active Decorate has significant improvements over just Decorate algorithm. And on 8 of these data sets, it produces much higher reductions than the other active methods. And these percentage reductions come in a wide range. The averages are summarized in the table below, but we can see that we can have some pretty high improvements in accuracy or in reduction in error up to about 70% as on the vowel data set.
Sorry, by significant, you say?
Not
on all data, you mean summed over all data sets? Or if it's a significant reduction, you mean statistically significant reduction?
So yeah, I do mean, so we do compute statistical significance, except we sort of have to define statistical significance, what it means to have statistically significance over a learning curve. So we constructed this alternate measure, which is sort of taking if the averaged error reduction across the curve is statistically significant for each of the pairs of the points, then we consider it to be a significant win. But yeah, they are. So yeah, mostly when I say significant, I do mean statistically significant. And here's a typical learning curve for one of the data sets where we see the active Decorate algorithm, which is in which is in blue, and the red line is just Decorate using random sampling. And what we notice is, active Decorate sort of selects examples in the order of its utility, and it's selecting more informative examples much earlier on in the curve. So there are basically two main aspects of any query by committee approach, and this is the method employed to construct the committee and the measure used to rank the utility of the examples. So far we've just looked at different methods of constructing committees, basic bagging, boosting, and Decorate, and we've ranked examples based on terms of the margins on these examples. But an alternate approach is we could use some information theoretic measures such as Jensen-Shannon divergence to measure the utility of acquiring the labels for an instance. And here the JS divergence is just a measure of the similarity between different probability distributions. So a little more details here. So given PIX as the class probability distribution predicted by the ith classifier for an example X, we can compute the JS divergence of an ensemble in the following way, which is basically the entropy of the mean distribution minus the mean of the entropies of the different distributions. And I won't go into the details here, but basically higher values of JS indicate a greater spread in the predicted class probability distributions. And the JS divergence of a distribution is 0 only if the different distributions are identical. So we ran our experiments as before, comparing this alternate measure of utility with our original margins measure. And in this table, we sort of summarized the two methods in terms of both data utilization and the reduction in error. And what we noted was that in terms of data utilization, they seem to be equally matched, but on error reduction, margins seem to be more effective. So in general, we would recommend using margins as the measure of utility here. And the reason why we think these results occur is in using JS divergence, we sort of select examples that are targeted at reducing the uncertainty in the predicted class probability estimate. And this only indirectly sort of helps us improve accuracy. Whereas if we use margins, we are focusing more directly on actually determining the classification boundary or the decision boundary. However, there are various applications where you want to make cost-sensitive decisions where it's actually critical to have accurate class probability estimates. And so our conjecture in this work was that if this was the case, it would be more beneficial to use JS divergence to improve class probability estimates. And yes.
Does all the ensembles computing compare class probability? Just counting the number of classifiers that go that way?
Well, basically, each of the underlying classifiers produces a distribution. So each of the decision trees produces a class probability distribution, and we average those to make a decision for the committee. But when you compute the JS divergence, it's the JS divergence of each of the distributions made by each of the classifiers. Yeah.
Sorry, how many classes are in ensembles? Do you have variation from 2 to?
Well, I could flip back to the dataset slide, but I mean they vary quite a bit. But I mean it's probably between some binary classes to up to maybe 60 classes is probably as high as it goes. So we actually recently have verified this conjecture that you want to use JS divergence if you want to maximize class probability estimates in an active learning setting. So now I'll move on to our third setting, which is what we call active feature value acquisition. So far we've looked at active learning where you have unlabeled examples and you can acquire labels for these instances. The alternative is in many tasks you actually have class labels for instances, but the instances themselves might be missing feature values. Right? And often these values can be acquired, but they can be acquired at a cost. And the motivating data set that got us started on this problem is the ComScore Jupyter Media Matrix data. And what this is basically information from different online retailers about a customer's behavior and purchases on their websites. So each of the retailers, such as Amazon or Priceline, have information about a customer's behavior on its own website. And this is private information that they have for free. But the retailer can also acquire additional information about a particular customer aggregated over other websites. And so these can be thought of as initially missing features, which can be acquired at a cost. And the task is then to predict whether a customer would make a purchase during a session. And basically we use this to determine when to make promotions, offer promotions to a customer. So in general, ignoring instances that have missing data would often lead to inferior models. Whereas the alternative of acquiring complete information for all the instances is often prohibitively expensive, or in some cases just unnecessary. So therefore, it's a very important task to be able to identify the instances for which acquiring complete information would be the most beneficial to the current model. Right. So here's a more formal definition of this task, which we call active feature value acquisition. And here we assume, again, a classifier induction problem represented by this matrix, where each instance is represented by n features and a class label. And for all instances, we know the values of a particular set of the attributes, and we also know the class labels for all of these instances. However, for the other set of instances, some of the values may be missing, and basically the entire set of these missing values for an instance can be acquired at a cost. Right? And so the task is then, given a feature acquisition budget, we want to identify which of these instances do you want to acquire all the missing values for. And you basically select instances such that acquiring this complete information would result in more accurate models. So we propose this very general framework for this AFA problem, which can be applied to any learning algorithm and any measure of utility, which I will discuss more in a later slide. And what we basically do is we maintain a set of complete instances which don't have any missing values, which may initially be an empty set. And we maintain another set with incomplete instances. And what we initially do is train our learning algorithm on both the complete and incomplete instances. Right? And this will produce a classifier. And based on this classifier and our measure of utility, we assign a score for the expected utility of acquiring the complete information for an instance. So basically, the score is the utility of acquiring all these missing values such that it would improve the accuracy of the current classifier. Yes?
When you train with reading complete features, do you do something like VM? Do you treat them like speaking?
So basically, we rely. So again, this can be applied to any learning method, and we rely on the underlying learner's ways to deal with missing values. So in particular, we apply these to decision trees, which C4.5 has a very specific way of treating missing instances. But other algorithms would do something like imputation, which maybe taking mean or mode predictions for the missing values, or EM or some method like that. But it's independent of what method the learner uses. So once we produce assign these utilities for each of these instances, we can again select the instance with the highest utility and acquire all of this data and transfer this over to the complete set. And we repeat this process until we exhaust the number of incomplete instances, or we have exhausted our budget for acquiring these values. So let me talk more about the measure of utility used. And in particular, we want to assign or acquire missing values only if it captures some discriminative patterns that don't exist in our data already, such that it would improve our current model. So we tried and we experimented with various measures of utility. Right here, I'll present just the error sampling measure, which is sort of our best method right now. And this measure is based on the following two observations. The first is that if an instance is misclassified by our current model, then acquiring more feature information for this instance is most likely to impact the model. So based on this, error sampling first focuses on selecting examples that have been misclassified by the current model. However, if all the instances are correctly classified, then it's most beneficial to look at instances that the current model is uncertain about. And here, this is based on the fact that in the absence of any discriminative patterns, we basically generate models that assign similar likelihood scores for different classes. And here, again, we use margins to measure our uncertainty, which is defined as the difference between the probability estimates of the two most likely predicted classes. So as I pointed out, our framework is very general. It can be applied to any learner, but we specifically present results here on applying Decorate with J48. And the reason that we use Decorate here is, as we've seen earlier, it does perform better on small training sets compared to the Bayes learner and other ensemble methods. And also we've seen that it's successfully applied to traditional active learning using the same measure of uncertainty, which is the margin measure. And in related work, which I don't present here, we've actually run studies that show that it's more resilient to missing features than the Bayes classifier and the other ensemble methods. This is for trees, yeah. So, a few details on the experiments. So we tested on 5 media matrix datasets and 5 UCI datasets, and I'll skip over some of these details because I think I'm running short of time. But basically, we compared our method error sampling to random sampling using Decorate. And this sort of is a summary of results over these 10 datasets, where similar to the active learning case, we compute these percentage reductions in error averaged over learning curves. And what we noted was, in most cases, we have significant improvements in accuracy over just random sampling. So those were the summary statistics on those datasets. We could also look at specific datasets, and another good indicator of the effectiveness of these different AFA approaches is the number of acquisitions required to obtain a desired accuracy. So for example, on one of the web usage datasets, this is for the company QVC, we see that to achieve a model that's 90% accurate, using error sampling, we require little more than 200 complete instances, whereas with random sampling, you would require 6 times this amount. And so this could translate to significant reductions in the cost of acquiring data. Yes.
The paradigm here, you pick a bunch of features. You pick an instance and managing all the features, or you're picking one particular new feature and managing for it?
No, you pick an instance and you get all the complete features. You get all the missing values that are in that feature.
But is that because the paradigm was? It seems like the other way of doing it is more refined.
Yeah. So basically, that was specific to this data setting where we actually had, the information is divided into, information that. So actually, maybe I should. So there's a subset of features, which a particular retailer owns all the information about one user, and you can buy the chunk from Media Matrix. You can pay them to get information of that. But yeah, the more specific setting is actually something that we've studied more recently. I'll actually come back to that in a second. So yeah, actually, this is where we talk about that. So our future work is in 2 major directions. The first is sort of looking at more complex settings than the 3 settings that we have looked at. So far we've looked at sort of the traditional active learning setting where we have we have examples with missing labels, and we've looked at this more novel active feature value setting where we have class labels but missing feature values. However, an easy extension here is to consider a setting where we could have both missing feature values and class labels. Also, as Eric was pointing out, in our current setting, we just assume that all the missing feature values for an instance can be acquired at once, and this was motivated by our data. But an alternative is to do a more specific, to solve the more general problem, which is being able to select a particular feature for a particular instance and acquire this value. And this is work that we've recently done, which will appear this year. Also, in all these methods, we've sort of just evaluated effectiveness of our models in terms of accuracy, but in most real-world data sets, accuracy is often not our goal. Like you could quite often have very different misclassification costs associated with the data set. For example, in fraud detection, there's a higher cost associated with a false positive flag there, and so we would like to be able to test our settings with different measures, such as, and different settings where we would examine different misclassification costs. Also, we have only looked at active settings where you have missing data or missing class labels, and these can be acquired at a cost. But an alternative is to just use the unlabeled data as itself by itself without acquiring these labels. And there's been considerable work in this area of semi-supervised learning, which we could borrow from here. We also have a few future work points on just the decorate algorithm itself. One is we would really like to test it on higher dimensional data, for example, on text documents. Also, we're really working towards developing a more sound theoretical understanding of decorate's effectiveness. And one direction in this one avenue in this direction is basically performing bias variance analysis of the different algorithms. And we've seen that looking at bias variance decompositions of error has been shown to be quite a successful or useful tool for analyzing different ensemble methods. So to conclude, we presented this algorithm decorate, which produces more effective diverse ensembles by manipulating a set of artificial examples. And in particular, we've shown it outperforms both bagging and boosting for small training sets. We've also presented the active decorate, which is an effective approach for selecting unlabeled examples to be labeled in an active learning setting. And by this approach, we can do significantly better than decorate with random sampling, and also we do better than competing active learning methods here. And we've also presented a general framework of this more novel problem of active feature value acquisition. And within this framework, we've proposed and tested this a particular method that shows significant improvements than random sampling. So to just summarize all these points, we've basically looked at different methods to learn more accurate models than existing methods with a reduced supervision, and this often just translates to lower costs of data acquisition. So, up for questions. Yeah.
About the
yeah.
So you example of probability,
Yeah.
and you get some probability that's member is the class membership. And your margin is the difference for the probability of the class membership of, say, positives versus negatives.
Yes.
So if you happen to have examples that are easy to classify based on the available features and they're strongly positive, right, then that wouldn't help. So if I give an example, right, because it's going to be a margin.
Yeah.
So how come that doesn't help?
So yeah, so we're actually selecting the smaller margin.
The smaller.
Yeah. So it's yeah. So yeah, you want to do just the opposite of that. Yeah.
So this is doing classification tasks. Do you think if you were doing probability estimation or regression or something, that instead of picking the lowest margin, which is more of a discriminative measure, that you would pick, like maybe the JS?
Yeah. So you mean specifically for the active feature value acquisition, or
for either of them?
So for the active learning, we actually so in ECML we have a paper which basically is active learning for class probability estimations, where we show that using JS is better than margins in that case. So yeah, it is. Yeah.
I have a pragmatic question. I mean, for all this active learning, why was your personalization have a great example?
Yeah.
The cost of user, but that assumes a constant labor and cost, right? So you can think of maybe the samples that are most informative are also the hardest for users to label. Has anybody looked at that? I mean, is there a relation between useful? It would be bad if there was useful and expensive to label.
Yeah. So I mean, yeah. This unfortunately, I don't think anyone has looked at this, but this is specifically concerned, especially when for active learning in natural language processing sort of domains, where where they're really coming up with path trees for some examples is a lot harder than for other examples, and typically those are the ones that are the difficult examples. And I know one of Miles Osborne's students are looking at Miles Osborne at the University of Edinburgh. He's sort of interested in looking at this, and he's actually also looking into using decorate for his methods. But I don't know about a specific published work on looking at different costs of labeling. Yeah.
So as far as selecting these artificial samples,
yeah,
it seems that if you were to, for example, if you had the discrete universe, right, you could just list all the artificial examples.
Yeah.
Right? So what you're doing here, you're effectively sampling from this set. Is there a good way of doing the sampling? I mean, do you have any recipes for doing that?
For generating the artificial example? No, we actually haven't. I mean, basically, we do. I don't think actually modeling the artificial data any better is going to get you too much more. So,
you decided your automated algorithm to how you select the artificial data.
what we did is we did compare our artificial data construction with using unlabeled data instead, which is actually just from the training distribution, and there isn't much benefit to doing that. So the simple artificial examples is actually quite effective. And so we don't actually, and basically there is a cost associated with constructing these examples at each iteration. So we don't really want to make that any more complex, and it seems unnecessary because we get good results without it. Did I finish answering?
Just a follow-up.
Yeah.
If when you give these artificial examples and then you train another classifier, and then you test to see if you're going to add it to the ensemble. If you don't add it, can you generate another set of artificial examples?
Yeah, we do.
Doing that so you find one that's good enough to add?
Yes. Because, I mean, otherwise you would end up with the same, in most cases, these are deterministic learners, so you would end up with the same classifier. This is all on the training set. So basically, we could have a cross-validation set, but since our focus is on small training sets, that's where you would lose out if you set some aside for testing. Cross-validation, sorry.
Well, to that, you're using C45, right, which builds a whole tree and trims back to make it regularized.
Yeah.
If you just built the tree and used it, you'd always, for example, get zero training errors. It seems like it's like decorating the line of C45 to generate those training errors. Have you ever tried it? Have you ever tried decorating it with not C45 as the base layer? Like little trees where you don't trim back. Because then it would seem like you always add a classifier every time, because you would always have zero training errors.
Right. We have, so even in C4.5, if you turn pruning off, there is some collapsing of leaves that goes on inside. So we have tried turning pruning off, but I don't think it's not completely fitting the data the way you're saying. But I guess a simple answer to the question is no, we haven't tried something that would fit it exactly and without pruning at all. But yeah, there's a good guess.
Well, what is the effect if you don't perform that test? You just add what the classifier that gets learned, regardless of whether it's information.
Yeah, so we have actually tried. We have run these various ablation studies, and it doesn't hurt a lot, but in some cases it does hurt, and so that's part of the reason we have the rejection criteria.
This is a high-level question. So the biggest boost in gain is for very small data sets, the active data set. So do you have an example, a practical example of where that really kicks in? It's very expensive to label a 7th guy.
A practical example. So basically, most of my work is I've just applied these on generic UCI data sets. So, by practical example, if you mean, have I applied in a real world domain where I've been a practitioner? No. But this is one of the things I would like to do. And yes.
Not familiar with the UCI data, but it seems the accuracy of the classification is very high. They're 90% on examples that you saw.
Yeah.
I know, that's amazing. You have 6 classes and so on. Have you tried this for, worse sensitive ambiguations? Cognitively available, or first check like 67% to see whether it helps very much?
No, but I'd be glad to try it on other data sets as well. But the cover? Oh, no, I haven't. Would you recommend that as a good Okay, yeah, no, that would be. So basically, we have a set of data sets that have been converted into Weka format, and there are 33 of them, and it's easy to run on these things. So, but if you have specific recommendations, then it's good to test on. Yeah.
So I guess this is sort of related, just a high level. Now that you've done this work and you see that On some data sets, you get a lot of improvement.
Yeah.
You know, and you don't have much data. On some, you don't have much improvement. Do you just have some intuition about what characteristics of data sets believe to be active learning really useful versus not?
Oh, on the active learning front?
Yeah. Or the, what do you call it?
No, well, we haven't actually studied well, specifically characteristics of data sets. That would be something interesting to look at. But just looking at the various data sets myself, I haven't found like a very consistent patterns that can be characterized by just the type of data or the feature values and things like that. But
you didn't have anything like if there's a class problem, then it doesn't help, or if it's really hard, then it helps.
We didn't notice such patterns. So we've sort of looked at these, but yeah, it's not consistent.
Great, thank you.
Thanks.